You know when you mix something in water, watch it sink to the bottom, and just think, well, that's insoluble? It turns out there is so much more going on than what we can see. We're about to pull back the curtain on a hidden microscopic dance that's happening all the time, even in that seemingly boring, static mixture.
So here's the plan for this explainer. First, we're going to blow up the whole idea of insoluble. Then we'll zoom in on what I like to call the solubility dance. After that, we'll get into the math with a magic number, KSP, and learn how to mess with the dance using the common ion effect and even pH. And finally, we'll use all this knowledge to predict if a solid is going to form in the first place. Let's do it.
All right, let's kick things off by taking a closer look at that word we throw around all the time, insoluble. Okay, this is a scene right out of every chem lab, right? We've got some calcium carbonate, which is basically chalk, and we've dropped it into some water. And just like you'd expect, most of it is just sitting there at the bottom, looking like it's doing absolutely nothing. But here's the big question, the one that gets this whole thing started. Is it really just sitting there? Is it actually static? Or is there a whole secret world of activity that we just can't see?
To answer that, we've got to zoom in. No, I mean way, way in, to see the incredible microscopic dance that's really going on. So here's the scoop. Right at the surface of that solid chunk, there's constant action. Individual calcium and carbonate ions are literally breaking away, escaping into the water. But at the very same time, other ions that are already out for a swim are bumping back into the solid and locking back into place. It's a non-stop two-way street. And of course, we've got names for these two moves. When the solid breaks apart into ions, that's called dissolution. And when those ions in the solution find each other and snap back together to form a solid, that's precipitation. It's this continuous back and forth.
Now, when the speed of ions leaving the solid perfectly matches the speed of ions returning, the system reaches a beautiful state called dynamic equilibrium. And this is the whole secret. Even though to our eyes the pile of chalk at the bottom isn't shrinking or growing, that microscopic dance is still happening like crazy. The action hasn't stopped, it's just perfectly balanced.
So if we have a balanced process, you know what that means, right? We can describe it with math. And that brings us to KSP, which you can think of as the rule book for the dance. KSP stands for the solubility product constant. And what it is really is just a single number that tells you exactly how soluble a substance is. It sets the limit, the absolute maximum amount of dissolved ions a solution can hold before it's completely full.
And writing the expression for it is pretty straightforward. For our calcium carbonate example, the KSP is just the concentration of the calcium ions multiplied by the concentration of the carbonate ions. But wait, you might notice something's missing. Where's the solid, the CaCO3? Well, in equilibrium math, we always leave out pure solids because their concentration doesn't really change.
Now, the awesome part about KSP is that if you know its value, which you can just look up in a table, you can calculate the precise solubility of a compound. It's basically a four-step recipe where you solve for a variable x, and that x tells you exactly how many moles of your solid can dissolve in a liter of water.
Okay, things are about to get interesting. What if we could rig the system? What if we wanted to force something to be less soluble? Well, it's time to crowd the dance floor.
Check out these two beakers. On the left, we're dissolving some calcium fluoride in pure water. Pretty standard. But on the right, we're trying to dissolve it in water that's already full of fluoride ions from a different salt. And whoa, look at that. Way less of the solid is actually dissolved on the right. So, what gives?
Well, there's a name for what you're seeing. It's called the common ion effect. And it's simple. If the solution already has one of the ions that make up your solid, in this case fluoride, that solid is going to be a lot less soluble.
But why does that happen? It all comes back to a superstar rule in chemistry called Le Chatelier's principle. Think of our equilibrium like a perfectly balanced seesaw. By dumping in extra fluoride ions, we've just added a ton of weight to the product side. The system hates that. To get back in balance, the seesaw has to tip back to the left, towards the reactants, which means forcing more ions to become solid again.
So we can add an ion. What other tricks do we have up our sleeve? Well, let's see what happens when we give this dance a little acidic twist by playing with the pH. Now this trick works like a charm when one of the ions from our solid is a weak base. Magnesium hydroxide is a perfect example. It's actually the active ingredient in lots of antacids. It dissolves into magnesium ions and hydroxide ions. And hydroxide, OH-, well, that's pretty much the poster child for a base, right? So,
What do you think happens when we start adding acid? Those H+ ions from the acid are on a mission. They immediately hunt down and react with the OH- ions from our dissolved solid. And what do they make? H2O. Yep, just plain old water.
And guess what? This is Le Chatelier's principle all over again. By adding acid, we are actively removing a product, those OH- ions, right out of the solution. It's like taking weight off the right side of our seesaw. The system freaks out and immediately shifts to the right to replace what was lost, which means more of the solid magnesium hydroxide has to dissolve. It's pretty cool, and it's actually why things like acid rain can slowly eat away at limestone and marble statues.
Okay, we've explored the dance, we've learned how to manipulate it. Now for the grand finale. Let's put it all together to make a seriously powerful prediction.
To make this prediction, we need one last tool. Meet the reaction quotient, or QSP. Now it looks and feels almost exactly like KSP. You calculate it the same way, but there is one massive difference. KSP tells you where the system is at the finish line, at equilibrium. QSP is a snapshot. It tells you where the system is right now, at any given moment.
And by comparing our snapshot, QSP, to the finish line, KSP, we can predict the future. It's actually super simple. If your Q is bigger than K, it means the solution has too many ions. It's supersaturated. So a solid is going to crash out. A precipitate will form. This is exactly the chemistry behind things like kidney stones. If Q is less than K, the solution can still hold more ions, so nothing happens. And if Q happens to equal K, bam, you're perfectly balanced at equilibrium. So that insoluble chunk of solid we started with, turns out it wasn't just sitting there at all. It's part of a constant, vibrant, hidden dance of equilibrium. And that just leaves you with this incredible thought, doesn't it? If this dance is happening in a simple beaker, what other invisible, balanced processes are shaping our world all the time, from the formation of caves deep underground to the very chemistry inside our own bodies? What else is going on right under our noses?